Okay, so here we have a problem. It says a lab experiment produces the interference pattern shown. And then it asks a bunch of questions. So the thing to note is that one of the things we know is, let me just make sure my pen is on, is that lambda is about 633 nanometers, and that's red, right? So this is red. Um, and so it's asking us what happens for the first, call this one A, B, and C. And for A, it asks, so what happens to the fringes if the screen is moved farther away from the slits? So we can do this two ways. We can draw a picture and then just do it by eye, right? So here are my fringes, or here are my slits, and here's my screen. And let's just say I'm looking at so if this is the central fringe, say I'm looking at this fringe. So this is my 0, I'm looking like that. Um, so I've got like a fringe here and a fringe there. And it's saying if the screen is moved farther away from the slits. So what happens then is so this is my L. And so let's say I move it back to here, right? We know the only thing that changes is the screen is moved away. So we know that so if I say d sine theta is equal to m lambda, my d stays the same, my theta stays the same, my lambda stays the same, my m stays the same. So what's going to happen? Well, if all I'm doing is moving it back, then this just gets projected up here like that, right? So that gets projected up there like that. And so my L gets bigger, so it goes out to here. And so something does happen. So what's going to happen here, my theta stays the same, but what's going to happen is my fringes are going to be spaced farther apart. So fringes are spaced farther apart. Right? So that's because I'm going to now have the fringe that was here, say m equals 1, is out here. So all of my fringes are going to have a bigger spacing between them. And we can also think about the other equation that we know, and that's tan theta is equal to y over L. And so here, my theta stays the same, but if my L gets bigger by moving the screen out, then my y has to get bigger in order for tangent theta to stay the same. So that would make sense that if y gets bigger, that means that the distance between the fringes is going to get bigger, and so I'm going to have a spread of the fringes. So that's how you figure out A. So B, it's asking us what happens if a green light laser is used. So I'm going to replace my red with green. So green, I know, is lambda's about, say, 550 nanometers. So I know it's less. So if I say d sine theta is equal to m lambda. So what am I changing? I'm changing lambda, and I'm making lambda go down. So I know m isn't changing. I'm going to still look at like the same fringe that I'm interested in. D isn't changing. I haven't changed the spacing between the fringes. So that must mean my theta goes down. So if my theta goes down, that means this first fringe and the central fringe get closer together. So the fringes come together. And then C, what happens if the slits are moved closer together? So we'll use the equation again, d sine theta is equal to m lambda. So we're back to red again. So our wavelength isn't changing. Let's say we're red, so that's a constant. I'm still looking at the first fringe over here, so that's a constant. If d decreases, then that must mean sine theta increases. So my fringes are spread apart.